Hello again. Today we're on location in my little corner of the shed again, and in this video we're going to cover the collimation of collimators. Quite a few people have got one of these, which is a laser collimator. We'll look at it a little bit closer later on. And the thing is that we tend to assume that once we've bought a laser collimator from the shop and it arrives that it's all nicely collimated and pointing straight and everything, and it's just not always the case. So we'll just come in a little bit closer and I'll just show you a couple of things. Starts off by just taking a look at my collimator. This is just a standard Antares laser collimator, but it does have a couple of little advantages. Firstly, it's a symmetrical design, which will become apparent in a short while, but also it has, if you look closely, you can see that it has collimation adjustment bolts in it. Behind there are some small Allen screws that adjust the angle of the laser diode inside this unit. Now, a very quick and dirty test to see if your laser collimator is actually collimated is to slide it into your focuser and just tighten it up so that you've lost the play, but that you can still rotate the collimator in your focuser. Now, what you do is you look down your telescope, watch for the laser red point on your mirror, and as you rotate your collimator, that red dot should stay exactly still. If the red dot's presenting a circle, it's drawing a circle like so, then 9 times out of 10 it's your collimator that's out. So what we'll do next is just go on to how to actually collimate it. We're going to need a really sophisticated tool for this, and it's this. This is actually made from plumbing parts. This design, it's an absolutely ingenious design. It was first shown to me by Steve Richards, the author of the book Making Every Photon Count, the astrophotography book. And basically what it is, it's 4 T-pieces, like so, 2 90-degree elbows, and just a couple of pieces of pipe and pushed together into that design. Now what that gives us is a V-block, which when set on a surface you can put the collimator into it and rotate it, and you know that it's going to stay in that same spot. We're not going to change any of the angles or anything, just the rotation. So we'll just look at this in use. Okay, so we've got a fairly solid level surface here, and we're going to just use our block system like this, our V-block system. Now what I would recommend is you also need a very technical piece of kit. We call it blue tack in the UK. You've probably got some sort of similar product wherever it is that you live, and you know, I just have no idea what they call it. But what we'll do is we'll stick these blocks down with pieces of blue tack, because when we're doing the adjustments we don't want this to move at all, and it will slide about on your surface just in normal use. But the addition of a couple of pieces of blue tack like so just makes everything sit nice and solid. Then what we want to do is take our laser collimator and sit it in the blocks like so. Next we need a distance of probably about maybe 4 meters is recommended. Now you might think, oh, but my telescope's only 1 meter long, so won't 1 meter work? And the answer is no, because your telescope's actually 2 meters long, because your light comes in, goes all the way down to the bottom and comes back again. So if we go at 4 meters, you know, we're just making sure that we're fairly accurate. So what we do is we place our collimator on our little blocks like so, switch the collimator on, and obviously we need to be pointing at a wall the correct distance away. Now what I like to do is I like to use a piece of tape, and we'll just show you that part now. Well, we've made another discovery, and that is that my camcorder doesn't like laser light, and it's making it look absolutely huge on the wall, the spot that it's presenting there. But what we do is we place a piece of tape like so. You can even use a piece of paper, sort of a piece of A4 paper, and just draw on it. And I make a mark on the tape where the spot hits. Now what we need to do next is to rotate the collimator in those blocks and check for any movement. So that's what we're going to do next. Right, as we now rotate the collimator in the block, the dot should be staying stationary and not presenting a circle. Again, like I said, if it is presenting a circle, it's out of collimation. As you can assume, it's quite a fiddly process, this one, and it's time consuming, and it's a little bit similar to when you're trying to set up your secondary mirror in a Newtonian, and you know, it can take, you might get it in like a couple of minutes at first go, it might take you an hour. Now some people might prefer to use a piece of A4 paper, just blue tacks to the wall. Now the idea is that as you rotate your collimator in your little V block, you mark the most outward point that it goes to from the point where you started. So mark again on your piece of paper the most outward point, then try and keep the collimator still and adjust it if you can manage it, and bring that dot, the red dot, to the halfway point between your two marks, which is the mark that you started and the most outward mark of the circle that it's presenting. Bring it to the halfway point, move your piece of paper on the wall again and centre your dot back into your middle point, or just put a fresh mark on your piece of paper. Repeat the process and do it again. And you know, sometimes like I said, it'll just fall in, and other times you can be there for ages. One important thing is to not assume that if you've got the most expensive laser collimator that it'll automatically be collimated when you get it. It's not always the case, and I've heard of laser collimators that cost well over £100 not being collimated when they've arrived. And if that is the case, if it's a brand new collimator, I wouldn't hesitate, just send it back and get a replacement. You know, unless you feel confident to either do it or basically want to, if you're just you know, an avid tinkerer. But it is definitely a process worthwhile, even if you just check your own collimator. And like I said, mine is just a cheap and cheerful Antares, and it serves me perfectly adequately. You know, there are other arguments about the centering, and then there's the Hortec argument with the self-centering thing, and I'm just not going to get into that at the minute, to be honest. But there it is, and that's how to collimate your collimator. So once again, I hope that's been of some help, and thanks for watching.